Hello everyone and welcome back. In this video I'm going to be going over a couple of problems involving Graham's law of effusion. So in the last video I had talked about the rate of effusion, and I've talked about Graham's law and things of that nature. So in this video I'm going to go over how to apply Graham's law. So this is going to be basic problems where you just need to know the equation using Graham's law. So in the first problem, you have an unknown gas that effuses at a rate that is 0.462 times that of nitrogen gas. So you've got an unknown gas that's going to be compared to the nitrogen gas, it's going to be traveling this many times that of nitrogen gas. So you can see that it's less than 1. So whatever this unknown gas is, it's at a slower rate compared to that of nitrogen. So one of the things you should be thinking of right away is this. Remember the relationship between speed and molar mass. So if this unknown gas is going slower, that means it's going to be a higher molecular mass. So that's what you should be thinking when you're calculating your answer, so that way you can verify it, check your answer, make sure it makes sense. So here they're asking you to calculate the molar mass of the unknown gas in grams per mole. That's important to note because the mass is going to come out to be, or the molar mass when you do use the equation is going to come out to kilograms per mole because of that R factor, or the R constant, which is going to be in joules, which has kilograms in it. So we need the molar mass of nitrogen. If you look that up in your periodic table, it's going to be 14. I want to make sure I get it exactly right. So it's going to be 14.01. Now, the great thing about this is, if you remember the equation, so let's say 14.01. So 14.01 is nitrogen. You're going to multiply that by 2, and so the total is going to be 28.02 grams per mole for the nitrogen. Okay, so you're going to have a rate, right? Rate of one gas over the rate of another gas, and that's going to be equal to the square root of the ratio of the molar masses. Now, what I said before, when you're dividing the rates equations, you get the reciprocal of the molar masses. I explained that in our last video. So you got to remember that it's going to be molar mass. So molar mass of gas 2 is going to be on top, and molar mass of the first one is going to be on the bottom. So if we replace this with N2 and let's see, I want to make sure I get this right. So that of N2. So if we have N2 here, and we have the unknown there, so the unknown is going to be 0.462 times that of the nitrogen gas. Okay, so when you write that out, this actually becomes a ratio. Okay, so the ratio is this many times that of nitrogen. So if I say, for example, so the unknown gas, so let's do the rate of unknown is going to be equal to 0.462 times that of whatever the rate, let's just say rate of N2, right? So that's what they're telling us. rate of the unknown gas is equal to this many times that of the rate of N2. So if I divide both sides by rate of N2, rate of N2, rate of N2, then I get this ratio is equal to this number there, which is what I have here. So that's going to be 0.462, and that should be in meters. Well, it's a ratio, so there's no units. So it's a unitless ratio. So now I can replace this. So 0.462 is going to be equal to the square root, and then I'm going to put in the molar masses. So this is going to be the unknown. Oops. So unknown molar mass is going to be on the bottom, and N2, molar mass of N2 is on top because they're reciprocal. They're going to switch it. And now I can put in the numbers. So I can put in, I don't have to do anything just yet. I can convert this to kilograms per mole right now and do it, or I can just plug this in and do it later. I'll just plug it in and do it later. So I have 28.02 grams per mole. And then here I have my unknown molar mass of N2. And now I can solve for the molar mass of N2. So that's going to come out to, so I'm going to square both sides to get rid of the square roots. So if I square both sides, I get 0.462. And then I'm going to square that equals, and so when I square that, so I square both sides. I square this side, I get rid of the square root, so then that becomes 0.213444, and that's going to be equal to 28.02 grams per mole over the molar mass of N2. So now I just do some algebra and I calculate the molar mass of N2. So I'm going to, let's see, I'm going to take 28.02 divided by this equals, and I get a molar mass, molar mass of this unknown gas, 131.2756 grams per mole. If you look this up in your periodic table, we've seen this number before. So 131.29 is xenon. So 131.29, 131.28 if we round. So this has got to be xenon gas. But they want the unknown gas. All right, so in grams per mole. So actually, we don't need to convert to kilograms because there was no need to put it in kilograms anyway. So that is the answer. We will round it to 4 sig figs, so this becomes 131.28 grams per mole. And that's it. All right, so what about this problem here? So in the second problem, they're saying, let's find the ratio of the effusion rates of these two gases. So again, we're going to use our equation. So here we have the rate, we'll do hydrogen, H2, is equal to, or I'm sorry, the ratio of the rate, so rate of hydrogen over the rate of, what do we have, Kr, is going to be equal to the square root of their molar masses, but the molar masses are going to be the reciprocal. So we're going to have molar mass of Kr on top, molar mass of H2 on the bottom. So notice that I have rate of H2 on top, rate of Kr on the bottom. If we're thinking about this, right, just in the same way here, I have a molar mass. So the molar mass of this, notice that this was less than 1. So rate of unknown over rate of N2. Since the rate is less than 1, that means that the denominator is larger than the numerator, right? So that means that the rate of N2 is going to be larger, faster than the rate of the unknown. So you should have gotten a molar mass that's larger because it's smaller. And that's what we got. We got a much larger molar mass. So same thing here, the way you want to look at this is like, okay, so if I have hydrogen on top and krypton on the bottom, so krypton is much larger than hydrogen. So this rate, I should get a rate that's less than 1. If I don't get a rate that's less than 1, then I made a mistake somewhere. Okay? And the only way I can make a mistake is maybe I flipped this, right? All right, so now I'm going to put in the molar masses. I can put in the molar masses. They can be grams per mole. I don't have to do any conversions because, again, this equation does not have the R value in it, so I don't have to worry about any conversions. Okay, so the molar mass of krypton, I think we just found that it was, oh no, that was Xena. Krypton is 83.80. So if we put this in, we'll have 83.80 grams per mole. And then hydrogen, that's 1.008, so that's going to be 2.016 grams per mole. Grams per mole cancel out, so we are unitless. So now all I need to do is take my calculator and divide. So I'm going to have and then I forgot to say that since the rate here, we have a larger molecule here, a larger atom here, larger molar mass, we have a larger molar mass molecule here and a smaller one here. So that means the rate for the krypton should be slower than that of hydrogen. So we should get a ratio that's greater than 1. So that's the way you want to think about it. So if we do this, notice here that we have a smaller denominator and larger numerator. So we are going to definitely get a number greater than 1. So that's perfect. So we're going to take our 83.80 divided by 2.016 equals, and we're going to take the square root of our answer, and we get a ratio of 6.447 yada yada yada. If we're looking at significant figures, we have 4 and 4, so we'll cut it off at 4. So that would be our ratio. Now, if you flip these, if you had the rate of Kr on top and the rate of Kr on the bottom, then what happens is that this 6.447 to 1 would be flipped. So you'd have 1 over 6.447, whatever that fraction is going to be. So you'll get a decimal number of some sort. So that's how you use Graham's law of effusion. It's a very simple equation. and may come in handy. So I hope this was useful. If you have any questions, put them in the chat. Tell me what you think. If you like the video, like the video, hit the bell for notifications, subscribe to the video, and again, put a comment in the video. I thank you for joining me, and I'll see you next time.